Hello, my name is Bruce Whitfield, and this is homework 6 for ECEN 423. The first question on the homework is to create a top-level system with a ALU and finite state machine component that is ran without feedback. So I first have an entity with two 4-bit inputs, a 2-bit selector, and a 4-bit output. The architecture for the ALU I have set up with a 4-bit signal that is going to store the value for the output. Next, I have a process for the ALU with a sensitivity list focusing on the two 4-bit inputs and the 2-bit selector. Now, for the case statement I use to cycle through the ALU's operation, if the selector is 0, 0, then the ALU will perform an OR operation on the two 4-bit inputs. If the selector is 0, 1, then the ALU will perform an AND operation. And if the selector is 1, 0, then the ALU will perform an addition operation. And if the selector is 1, 1, then the ALU will perform a subtraction operation. There are 4 operations within my ALU, and at the end of the process, I have output set to temp, and this stores the signal's value into the 4-bit output. Next, I have created a finite state machine for my top level system. My finite state machine has an entity with a 1-bit clock input, a 1-bit data input, a 1-bit reset input, and a 2-bit output. The architecture for the finite state machine, I've created a type called state type, and the state types are 0, 1, 0, S0, S1, S2, S3, and this is an enumerated type. And then I declare the signal, which acts as a register to hold my current state. I next have a process with a sensitivity list with the clock and reset. This if statement right here, it checks to see if reset is enabled. And if it is enabled, then it will reset the state to state 0, and the output is reset to 0, 0. This next statement is looking for a clock event with clock equaling 1. And this is because this is a system that responds to the rising edge. Next, I have a case statement, and this case statement is looking at state. So when in state 0, if the data in is 1, then it will move to the next state, and the data out will be 0, 1. If it does not have data in equal to 1 but 0, it will remain in state 0. If in state 1, if data in is 1, it moves to state 2, and data out changes to 1, 0. If data in is 0 while it's in state 1, it will remain at state 1. If in state 2, data in is 1, then it will move to state 3. Otherwise, it's just going to stay at the same state. And if in state 3, data in is 1, it will move to the next state, which is state 0, and it moves to the beginning of the sequence. This is the end of my finite state machine code. The next, I would like to look at the top level system. So for the top level system, I have the ports for the entity set up with the ports for the two components of the ALU and the component for the finite state machine. And so that's why the ports for the top level system has two 4-bit inputs, one 2-bit selector, and a 4-bit output, which is the ports for the ALU. And then the ports in the entity for the top level system has 3 1-bit inputs, clock, data in, and reset, and a 2-bit data out. And those are similar to the ports from the component for the finite state machine. Next, I have the architecture for the top level system. Right here I've declared the ALU component and list the ports for that component. And then the next component is for the finite state machine. The finite state machine's ports are set up right there. And then, so I have both of my components declared, the ALU and the finite state machine. And the last thing to do is instantiate my ALU component and my finite state machine component. Now, with all of that in order, it is time to show the test bench for the top level system. This is the entity for the test bench and the architecture for the test bench. Now right here are the signals that are the ports for the top level system. And right here is the component of the top level system, which ports are comprised of the ports from both of the components that make up the top level system. Next, I have instantiated the top level system component right here. And next, I am working on my test bench values. I start off by resetting, having reset enabled, and once the clock is at the rising edge, it will reset the state to 0, and it will reset the output from the finite state machine as well. Now moving down, that right here with the reset, this shows that the reset works. Now, this only responds to the rising edge. So when clock is 1 and D is 1, it will move to the next state, which is state 1. And then I move on, and at the next rising edge, it will move to state 2. And at the next rising edge, it will move to state 3. And at the next rising edge, it will move back to state 0. Now, because the top level system has a finite state machine and ALU component, that the data out is what is being fed into the ALU to know which operation to perform in which order. So, as the S, which stands for the selector, as the selector changes throughout this test bench, also will the data out coming from the finite state machine. Next, I would like to show the waveform. So, the waveform is going to definitely be minimized. Alright, so the waveform looks a lot like this. So, on this waveform, the A, B, S, and O stand for the two 4-bit inputs, the 2-bit selector, and the 4-bit output for the ALU. The clock, reset, D in, and D out represent the clock, reset, input, and output of the finite state machine. So, whenever clock is set to 0 and is set to 0, I have reset set to 1, and the system starts off in state 0. And so whenever the clock transitions, it remains with in state 0, and this is because you would think, since D is 1 and clock is 1, that it would move to the next state, but it is set, reset is enabled, so the selector for the ALU is 0, 0, and the 2-bit output for the finite state machine is also set to 0, 0. Now, at the next rising edge, with the input for the finite state machine set to 1, it moves to state 1 in the second operation in the ALU, and it moves to state 1 inside the finite state machine. At the next rising edge, it moves to state 2 in the finite state machine, and it moves to state 2 to operation 2 or 3 in the ALU. Next, at the next rising edge, the operation being performed in the ALU is the 4th operation, and the 2-bit output for the finite state machine is at 3, which would put it into the 3rd state. At the next rising edge, the operation for the ALU is returned back to its first operation, and the ALU knew that it's back to the first operation because of the output of the finite state machine being in the 3rd state. So if this test bench was a little bit longer, you would see that the output coming from the finite state machine would also transition back to its first state. This is all. Thank you very much.